Hello dear classmates, welcome to the VLSI testing class. In this chapter, we will introduce the part 2 of logic built-in self-test. This slide is a review of a chip-level BIST architecture. There are three major components: a BIST controller, a test pattern generator, and the output response analyzer. We already introduced a test pattern generator in part 1. So we are going to introduce the output response analyzer and the overall architecture in this chapter. Here is a famous quotation by Chinese Confucius. He said that what the superior man seeks is in himself. What the small man seeks is in others. I think this is a very wise quotation, suitable for this chapter, because in built-in self-test, an output response analyzer observes CUT output responses. The area of this ORA is very small, but it must make a correct pass-fail decision. In the part 2 of the BIST lecture, we will first introduce the ORA, and then we will introduce some useful BIST architecture. Then we will discuss some issues and the possible solutions of BIST. Finally, we will conclude this chapter. So, what is an output response analyzer? An output response analyzer compresses CUT output responses into a very small signature so that it can be stored on chip. At the end of the test, we compare the signature with gold signature, which is the signature of a good circuit. And then we can determine whether this CUT passed or failed the test. As is shown in this figure, the job of ORA is to compress the output responses into a small signature, so the ORA can be regarded as an on-chip compressor. At the end of the test, the signature will be compared with the gold signature. If they are the same, the CUT passed the test. If they are not the same, the CUT fails the test. This is why the ORA is also known as a signature analyzer. So, what is a good ORA? First, it is required that the signature must be as small as possible so that the signature can be stored on chip. Second, it must make a correct pass-fail decision. That is to say, there is very small possibility of aliasing. We will explain this idea in the next slide. Third, a good ORA must be very small in area, so the overhead will not be too much. Finally, when the CUT failed the test, the ORA can support diagnosis. Sometimes it's very difficult to meet all these requirements, so the design of ORA is a challenging job. So what is aliasing? Aliasing occurs when the signature of a faulty output is the same as the signature of a good output. As is shown in the following figure, on our left hand side, this circle represents the output space. On our right hand side, the smaller circle represents the signature space. Because the size of output space is much larger than the size of a signature space, so the output response analyzer performs a many-to-one mapping. In this figure, each dot represents an output of a CUT. The good output of the CUT is compressed into the good gold signature. The other dots of the circuit represent faulty CUT output. They are compressed into blue dots, which represent bad signatures. Because the bad signatures are not the same as the gold signature, so we can easily tell them apart. Even though these two bad outputs are mapped to the same signature, this is not aliasing because we know that they are bad chip. However, for this faulty CUT, the faulty output is compressed into the same gold signature. This is aliasing because we don't know whether this CUT is good or faulty. Aliasing causes fault coverage loss and test escapes. That means a defective circuit can pass the test. This is a very bad thing for built-in self-test. Aliasing depends on many factors such as the CUT and the fault test patterns and the output response analyzer structure. To perform exact analysis of aliasing is sometimes difficult, but we don't actually need an exact analysis. We can just use probability analysis to analyze ORA. The probability of aliasing can be defined by this following equation. PAL is equal to the number of faulty output that generate good signature over the number of total faulty output. This number is between 0 and 1. A good ORA has very low probability of aliasing. Here is a small quiz for you. Suppose we have this CUT which has two outputs. Suppose the good output is 0, 1, and we use an inclusive OR gate as our ORA. So, what is the good signature? Question number 2. What is the probability of aliasing of this ORA? Suppose that 4 possible CUT outputs 0001, 1011 are equally likely. Now please pause the video and do the exercise. Okay, have you got the answers? The first one should be easy. The inclusive OR of 0 and 1 is 1. So the gold signature is 1. For the second question, the equation of PAL is equal to this. In the denominator, we have total number of faulty outputs, that is 3, including 00, 1011. These 3 are faulty outputs. Only 1 is correct output. In the numerator, the number of faulty output that generate gold signature. For output 00, the signature is 0. so there is no aliasing. For output 1, 1, the signature is also 0, so there is no aliasing. For output 1, 0, the signature is 1. This is aliasing. So the probability of aliasing can be estimated to be 1/3. Now, in the following of this video, we will introduce some simple output analyzer. This include duplication, checksum, once counter, and transition counter. This slide shows a simple idea of ORA, which is duplication. Suppose this circuit here is our CUT circuit under test. To test this circuit, we simply duplicate this CUT and we compare the output of those two CUT. If they are the same, the circuit passes the test. If they are not the same, then we generate an error signal, which means the CUT fails the test. The advantage of this ORA is that the aliasing probability can be very low. It is also good for online built-in self-test. However, the area overhead of this ORA is very large, so it's not very practical, except mission-critical systems. A reverse operation is another idea of ORA. Suppose we apply the test pattern to the CUT which performs the function f, and then we take the output of the CUT and performs an inverse function f-1. The output of this f-1 should be the same as the input test pattern. If they are the same, the CUT passes the test. If they are not the same, then the circuit is faulty. This idea is good for both online and offline BIST, and the aliasing probability can be low. However, we may not be able to find the inverse function f-1, so this idea is not generally applicable to all the CUT. Here is another simple idea for ORA, the Parity Checker. As is shown in this figure, we have an exclusive OR gate followed by a D flip-flop to accumulate the parity. The signature is equal to the inversion parity of the CUT output. It can be odd or even. For a good CUT output, 0, 1, 1, 0, 0, the inversion parity is 0, which is the good signature. However, for faulty CUT number 1, suppose that 1 bit is flipped from 1 to 0. So the inversion parity of this faulty output is 1. We can detect this fault. There is no aliasing. For faulty CUT number 2 output, however, suppose that there are 2 bits flipped. So the inversion parity is the same as the good circuit. This fault is not detected, so we have aliasing. For this ORA, let's calculate the PAL. The number of total faulty output is equal to 2 to the power of 5. 5 is the length of the output bit stream, minus 1, which means the good output. The other 31 output bit streams are faulty. Out of these 31 faulty bit streams, there are 16 bit streams that has the same parity as the good circuit. And don't forget to -1. This one also represents the good output. So overall, we have 15/31, which is approximately 1/2 probability of aliasing. This is not a very good ORA because the PAL is too high. In this slide, we show a more sophisticated ORA once counter. As is shown in this figure, we use a counter as ORA. This counter counts the number of ones in the CUT output response, so the signature is equal to number of ones in the output. For the same example, suppose that the good CUT output is equal to 01100, which has 2 ones in the output bit sequence, so the good signature is therefore 2. For 40 CUT number 1 output, we flip 1 bit, so the output sequence is 01000, which has only 1 1. We can detect the fault because the bad signature is not the same as the gold signature. There is no aliasing. However, for 40 CUT number 2 output, 01010, which also has 2 ones in the output, so the fault is not detected and there is aliasing. So how do we analyze the PAL of this counter? The PAL of this counter can be expressed as this equation. In the denominator, again, is 2 to the power of m minus 1, where m is the output sequence length. In this example, because we have 5 bits in the output, so m is equal to 5. In the numerator, we have the combination of m choose n minus 1, where m is the output sequence length and n is the signature, which is the number of ones in the good CUT output. In this particular example, n is equal to 2. If we plug in these numbers of m and n, we would get combinatorial 5 choose 2, that is 10, minus 1, which is the good output. So eventually we would get 9/31 as the PAL of this particular analyzer. This is not very good, although it is better than the Parity Checker. However, it is still not satisfactory. And this slide shows a more sophisticated transition counter as ORA. This transition counter, as is shown in this figure, we have one D flip-flop which store the previous bit, and we have an exclusive OR that compare the value of the previous bit and the current bit. If they are different, then we have a 0 to 1 transition or we have a 1 to 0 transition. This counter is then incremented by 1. So the signature of this ORA is equal to the number of transitions in the output bit stream. For the same example, suppose that the good CUT output is 0, 1, 1, 0, 0. We have one rising transition and one falling transition. So the gold signature is therefore 2. For faulty circuit number 1 output 0, 1, 0, 0, 0. This bit stream also has 2 transitions. Therefore, the signature is 2 and we cannot detect the fault. This is an aliasing. For faulty CUT number 2 output 0, 1, 0, 1, 0. It has 4 transitions, so we can detect the fault. And there is no aliasing. So how can we analyze the PAL of this transition counter? We can use this equation. In the denominator, again, we have 2 to the power of m minus 1, where m is equal to the output bit sequence length. In this particular example, it is 5. In the numerator, we have 2 times the combination of m minus 1 choose n and the minus 1, where n is the number of transition in good CUT output. In this particular example, it is 2. The reason why we have m minus 1 is because if we have m bits, then there are m minus 1 possible positions for transition. For example, if we have 5 bits, then we would have 4 positions for possible transition. Therefore, we use m minus 1 choose n. If we plug in the numbers of m and n, we would get 2 times the combination of 4 choose 2 minus 1, which is equal to 12 minus 1. So the PAL of this particular transition counter is 11 over 31. Again, this number is still quite large, and we cannot accept this kind of PAL. In summary, in this video, we have shown output response analyzer, which compress CUT output responses into signatures. Aliasing occurs when the faulty outputs are compressed into a good gold signature. Aliasing is bad because it can induce test escape. We need to calculate the probability of aliasing, which is defined as the number of faulty output that generate good signature over the total number of faulty outputs. The number of PAL is between 0 and 1. Lower PAL indicates a better ORA. We also show different architecture of ORA, including duplication, parity checker, once counter, transition counter. They are either too large or the PAL is too high. These ORA are not good enough for our use. In the next video, we will show LFR-based ORA, which is much better than this simple ORA. In the last slide of this lecture, I would like to ask you an FFT for the transition counter. If you remember, the PAL of a transition counter is equal to 2 times the combination of n-1 choose n-1 over 2 to the power of n-1. There is a factor of 2 here. Can you tell me why there is a factor of 2? I can give you a hint. Please consider the polarity of transition. Thank you very much for listening.